So we've got Lake Blackstone water. It's being treated for the removal of color and turbidity in a conventional surface water treatment plant. Uses coagulation with ferric chloride. Also uses dual media sand filtration with disinfection by chlorine. What I want you to do in your group first is to draw a schematic of the plant showing all the processes, where chemicals are added, and where residuals, so sludge or water that needs to be treated, are produced. Okay, so think about this. I will either write on the sheet or come into your breakout room to kind of help you through that. On Monday, we looked at this problem here. So we have Lake Blackstone. It's treating water at a maximum daily flow rate of 0.88 meters cubed per second. It's about 20 mgd. Ferric chloride is used as the coagulant. Optimal dose was found to be 21 milligrams per liter. You're told that the average suspended solids concentration is 32 milligrams per liter, and the effluent suspended solids concentration from the sedimentation basin is 1.5 milligrams per liter. You're given the equations for the reaction of ferric chloride to produce ferric hydroxide, and that's what's precipitated. And the first reaction includes alkalinity in the equation. The second one here, or it does not include alkalinity. The second one does include alkalinity. We're assuming here that alkalinity can be estimated by the concentration of bicarbonate. So on Monday, I went through and we calculated the amount of ferric chloride required per day. We multiplied the dose by the flow rate and then used the appropriate conversions. And then ferric chloride is actually supplied as a liquid. So we then calculated the volume. Notice, because it's only 35%, in terms of mass, we actually need almost 3 times as much mass of ferric chloride. You're paying for water, basically, than what we calculated initially. We then calculated the amount of sludge produced. Notice we have sludge here from the suspended solids. So this is the removal of suspended solids. We then looked at the equation. So we looked at the stoichiometric equation. The amount of ferric chloride to ferric hydroxide is a 1-to-1 stoichiometry. So then we can calculate from that. So we start with our dose and we calculate the concentration of ferric hydroxide that is produced. Okay, so that's a mass. So we produce 20.8 milligrams of ferric hydroxide per liter based on the dose. What we then calculate, that's our mass of ferric hydroxide that we produce per day. And we add the masses from suspended solids plus the ferric hydroxide, and this gives us our total dry weight. Okay, so we have a solids content of 0.75%, and that's typical. The sludge solids have a specific gravity of 1.6, and now I want you to determine the volume of sludge produced. If you can do that, then the next thing I want you to do is to calculate the amount of alkalinity consumed, which from then you can determine the amount of alkalinity remaining. So hopefully that was helpful to kind of think through the processes. I'll draw the schematic. It's also in Monday lecture. But so we have raw water. First thing, typically water is screened in the scavenger hunt. One of the places you'll visit is right by the rapids. If you're on the south side of Campus and you're looking north towards the parking garage, you'll see that there is a large structure there with screens. That is actually a river intake. And what you're looking at are the bar screens. So that's to keep out large material, twigs, fish, etc., from entering into that intake structure, and then where it's pumped. So in that are actually pumps, and that water is then used for irrigation. So we have screens. We then go to rapid mix. So that would be where we would add the ferric chloride. We add our coagulant. We then allow the water to flow into a flocculation basin. So here we have slow mixing to allow those particles to contact one another, to aggregate, and then be large enough to be removed in the sedimentation basin. And that's where the sludge is produced. The effluent from that is then pumped into a filter. We may add filter aids. So for instance, if we need additional removal, we may add filter aids at that point. If we need a coagulant or a polymer, typically we're going to add that because we want to improve sedimentation. So we're either going to add the polymer here, or we may add it before sedimentation. But typically we would add it earlier. And then we have, from the filter, we then go into disinfection. So we would add the chlorine here, and then storage and distribution. Okay. So that is the process. Okay. I've mentioned this. I'm not going to go through all of this in the interest of time. I have recorded Monday's discussion, so if you want to go over that, it's on Monday's discussion. So we've calculated then the dry weight of solids that are produced. Okay, and that is 2,319 plus 1,584, and that is equal to about 3,900 kilograms per day. So that's our dry solids. You're told that the sludge content is 0.05%, and the sludge solids have a specific gravity of 1.6. So that's of the solid itself. We need the specific gravity of the sludge in order to calculate the volume. So that is simply 1.6 times 0.0075, converted percent to a fraction, plus 1.0, the specific gravity of water, times 1 minus 0.0075. So notice more than 99% of your volume is going to be water. And that gives us a specific gravity of 1.00. 0.45. The fraction of solids is equal to the mass of the solids divided by the mass of the solids plus the mass of the water. So we've said that the fraction of solids is 0.0075, and that is equal to 3,900 and divided by the total mass, which is just the mass of the solids plus the mass of the water. So if we solve this, we can calculate that the mass of the water is equal to 516,500 kilograms. Notice it's significant. So it's about 516 tons, metric tons of water. It's also why, and I didn't draw it, we didn't draw it, but we drew the sludge. That sludge is typically treated. We want to dewater that sludge as much as possible, because if we have to transport that sludge anywhere for disposal, we don't want to have to be paying to transport water. So then the volume of sludge is equal to the mass of our solids plus the mass of the water. This is in kilograms per day, times 1 over the specific gravity times the density . 1 over the density of water. And this is 518 cubic meters per day, which, just to give you this in gallons, it's about 137,000 gallons per day of sludge that we need to treat and ultimately dispose of. The last thing I asked you to do was to calculate the alkalinity of the water after coagulation. So we have ferric chloride plus, it's consuming 3 moles of bicarbonate plus 3 moles of water. This is the part of the reaction we need to worry about. So 1 mole of ferric chloride is consuming 3 moles of bicarbonate. And as I mentioned, because of the pH, we can assume that alkalinity is approximately equal to bicarbonate. So we're just looking now at stoichiometric ratios. So we have 0.129 millimoles per liter of ferric chloride. So if you look back at Monday's lecture, you'll see how we calculated that. It's just the dosage divided by the molecular weight of ferric chloride. We have 3 millimoles of bicarbonate per millimole of ferric chloride, and that is equal to 0.39 millimoles per liter of bicarbonate that reacts. So that's the amount of bicarbonate that reacts. Now, alkalinity is usually given in milligrams per liter as calcium carbonate. And notice that's given as 56 milligrams per liter as calcium carbonate. So we need to convert this to the same units as we're given here. So the change in alkalinity, this amount of alkalinity that's reacted, is 0.39 millimoles per liter. Bicarbonate, notice, has a charge of -1. It can either give up one proton or accept a proton. So it has an equivalent number of 1. So we have 1 millimole per 1 milli equivalent. Okay. And the equivalent weight of calcium carbonate is 50 milligrams per milli equivalent. Okay, so this is the equivalent weight of calcium carbonate. And that is 19.4 milligrams per liter as calcium carbonate. So the final alkalinity is equal to 56 minus 19.4, or 36.6 milligrams per liter as calcium carbonate.
Professor, can I ask how you got the 50 milligrams per milli equivalents?
Good question.
Is that just given? Yeah.
Okay, so if I calculate the molecular weight of calcium carbonate, that is 100 milligrams per millimole. Okay.
Okay.
Calcium has a charge, think of it this way, has a charge of 2+. Carbonate has a charge of 2+. Carbonate can react with 2 protons to produce carbonic acid. So because of that, N is equal to 2. So there were 2 equivalents per mole, or 2 milli equivalents per millimole. So the equivalent weight is equal to 100 milligrams per millimole. Okay, and then there are 2 equivalents, or we'll do this in millimoles, per millimole. Okay, so that is equal to 50 milligrams per milli equivalent. So that's the equivalent weight of calcium carbonate.
Gotcha. Thank you very much.
No problem.